Our focus in this lesson is Newton's laws of viscosity, one of the subjects we'll be treating under fluid mechanics. Fluid mechanics is the study of the behavior of fluids, both at rest and in motion. That simply means fluid could be at rest and it can be in motion. When it is at rest, we're going to study the behavior when it is at rest, when it is not moving, and then when it is in motion, we will exert some effort and understanding in that direction too. The term fluid means that something is capable of flowing and having no definite shape. So when you say something is fluid, it means that thing is capable of flowing and has no definite shape. Fluid refers to both liquids and gases. Gases are very compressible. Their volume change as pressure and temperature and can be given by this ideal gas law, PV equals nRT, where P represents the pressure, V represents the volume, N represents the number of moles or amount of substance available, R represents the gas constant, ideal gas constant, and T represents the temperature. So PV equals nRT is the ideal gas law equation that we have to pay attention to. This is very important. Liquids are practically incompressible. Hydraulics is one of the terms that we have to be familiar with, and it refers to the study of the behavior of liquids. In fluids, there are three types of important processes to observe. The first one is heat transfer, the second one is mass transfer, while the third one is momentum transfer. Let's take a look at each of these items. Heat transfer is given by this expression, Q equals minus K dt dx, where Q represents the amount of heat transfer, K represents the thermal activity, delta T will represent change in temperature, delta X will represent change in position. Okay, so as you can see from this diagram we have right at the bottom here, you can see we have X1 and then we have X2. X1 represents the initial position, while X2 represents the final position. Change in X will therefore be X2 minus X1. You can also see that we have the initial temperature 100 degrees Celsius and then we have the final temperature which is 50 degrees Celsius. What you will notice here is that there is a heat flow from the region of higher temperature to the region of lower temperature. Okay, what you would find out here is that we can easily find our change in T also from what we do have here, and K is referred to as our thermal activity. The T, the X, delta T divided by delta X is given as thermal gradient. At some point, you will be asked to evaluate the thermal gradient, the thermal activity, and so on and so forth. Mass transfer is given as this expression, J equal to minus D dr dx, which can also be equal to minus D multiplied by change in C divided by change in X. Change in C divided by change in X is referred to as concentration gradient. Don't forget, when we were talking about the heat transfer, we talked about the thermal gradient. Under mass transfer, we're talking about a concentration gradient. J is the net amount of material diffusing across a unit cross-section perpendicular to the direction of either movement or flow or motion. Here, the direction is chosen as X. D is referred to as the diffusion coefficient. Now, you will notice this minus sign here. This minus sign indicates that the material is transported in the direction of decreasing concentration. The same thing happens to heat transfer, where heat is transported in the direction of decreasing temperature. The next is momentum transfer. The momentum transfer actually is directly connected with Newton's law of viscosity. And then you see that we have tau. This symbol is referred to as tau, equal to minus mu. This symbol is referred to as mu. Tau equal to minus mu multiplied by dv dy, where v would represent our velocity and y would represent our position. And then dv dy will be referred to as velocity gradient. So we've talked about three different gradients. We've We've talked about the thermal gradient. We've talked about the concentration gradient. Now we're talking about velocity gradient. So let's say we have a solid here, and then we apply force F1 on this solid rod. And the force F1 is applied towards one end of the rod from the left, and then force F2 is applied towards the other end of the rod, solid rod, from the right. And both of them are compressing the rod. F1 and F2 in this case will be referred to as compressive forces. If the direction is reversed and then F1 from the right is pulling the rod to the right and F2 is pulling the rod to the left, it simply means that F1 and F2 in this particular case will be referred to as tensile forces or shear. So like we said earlier, dV dy is referred to as the velocity gradient. Mu is referred to as the viscosity, and then our shear force divided by area is what is referred to as tau. Tau is referred to as shear force divided by area. This is shear force, that's why we have S here, divided by the area, cross-sectional area, and then we have the shear stress, which is referred to as the tau. Shear stress can also be referred to as the opposing resistance. So shear force is always the force applied taking parallel to the fluid flow. Every physical quantity has a characteristic dimension. We're going to be looking at some of the physical quantities we're dealing with, their dimensions and their unit. The basic dimensions we're dealing with are the length, the mass, and the time. So we will represent the length with L, the mass with M, and then the time with theta. Velocity is usually given as distance over time. That will be length over time. So we have length over time, and then you can see we have L theta raised to power minus 1. This will be the dimension for velocity. We do know that length is measured in meters and time is usually measured in seconds. Hence, we can say the unit of velocity is going to be meters per second. In the case where the length is measured in feet, we can say we have feet per second. So these can be converted to several units depending on what you're working on and the framework of operation. Let's look at pressure. We've dealt with velocity, now let's look at pressure. Pressure is usually referred to as normal force over area, and this is also called normal stress. As you can see from here, 1 atmospheric pressure is given as 760 millimeters mercury. Hg here represents mercury, which is equal to 760 torr, which can also be equivalent to 101.325 kilopascal. This can also be converted to pound per square inch. This can also be converted to several other units depending on what you're working on. Most of the popular units of pressure are the pascal, kilopascal, and the millimeter mercury that we have here. Okay, torr is the unit of pressure applied by depth of 1 millimeter, and I told you earlier Hg represents mercury. Now when we talk about force and weight are similar. All right, we talk about weight when we are dealing with vertical motion, and then we talk about force when we are dealing with both vertical and horizontal motion, depending on the situation we are in. Okay, so W equal to mg. W represents the weight, M represents the mass, and G would represent gravitational pull or acceleration due to gravity. F equal to ma. This M still means mass, while A would represent acceleration. For the standard dimension, for the dimension of force, you can represent our mass with m. Our acceleration is equal to velocity over time. We know that velocity is L theta raised to power minus 1 divided by time. In this case will give us L divided by time squared, and this will give us L theta raised to power minus 2. So if we come back here and then we substitute the dimension of A into this equation, we have m multiplied by L divided by theta squared. We also know that area is equal to length times breadth, and if we are dealing with a dimension with the same length and breadth, then we can say length times length, since breadth is equal to length, and that would give us length squared, and that gives us L squared in this case. So pressure given as force over area will therefore be equal to ml theta raised to power minus 2, where this L theta raised to power minus 2 represents our acceleration, and then m is here, all divided by area. Area will be equal to L squared. Okay, if you just cancel out what we have here, 1L cancels 1L, theta raised to power 2 comes down. What you're going to have left is m over L theta raised to power 2. So 1 Pascal, or the unit of pressure, can also be given as kilogram per meters per seconds squared. This can also be given as the unit of pressure, and that is equal to 1 Pascal. So you can see we have the dimension of pressure right here, and then the unit of pressure right here. Having talked about the weight and the force, we can easily talk about work or energy. Work done is usually synonymous to energy, and that is given as force times distance. We know that our force is measured in Newton, so you can write N representing Newton, and then we have our distance measured in meters. Okay, so this simply means that the unit of work can actually be equal to Newton meters, and 1 Newton meters is equal to 1 joule. Okay, unit of work done or energy can be equal to joule, and it can also be equal to Newton meters, as you can see here. From the unit of force that we initially obtained, this can give us kilogram meters per second squared multiplied by meters, and that eventually gives us kilogram meters squared per second squared. So this gives us the unit of energy, and this gives us a dimension of energy. From the previous explanations we had, you can easily work on all of these, substitute the dimension of force we obtained, put it here, and then put the dimension of length or distance here. You would obtain this dimension, and then from the units, you just put the 2 units of distance, you put the 2 units of force and distance together, and then you obtain this particular unit for our energy. All right. Now let's quickly talk about a continuum hypothesis. We will start by talking about density. Density is a function of position due to molecular variations, and it can be given as mass over volume. So this is density symbol here, which is equal to mass over volume. Okay, so we can also have it as change in mass divided by change in volume. So as change in volume tends to 0, the density will continuously change. The gas molecules are discrete particles which are moving in space with time. Therefore, we can say that we have to consider a minimum value for the change in volume, which is usually given as epsilon cube raised to power 3. So we've mentioned the fact that the minimum change in volume is equal to epsilon raised to power 3, where E is still large compared with the mean distance between the molecules. Okay, so if you look at what we have here, these are molecules. Let's assume these are single molecules of oxygen gas. These are oxygen gas molecules. Okay, here time is equal to 0, and then they are and the volume is very small here. When time is equal to 10, what can you notice? When time is equal to 20 seconds, what can you notice? You will keep noticing that as the volume tends to 0, the density continuously changes. Mass of a single molecule is given as m. So what you will notice here is that we have 5 molecules here of oxygen. Okay, so you have 5 molecules divided by V. Here the density will be equal to 2 molecules divided by V, and then here you have 0 molecules divided by V, and that definitely gives us 0. Okay, so as the volume tends to 0, what usually happens is that the density continuously changes and also tends to 0. Now let's quickly talk about a specific weight, which is given by the symbol here. Specific weight is the weight of substance per unit volume. So that means you will see that specific weight is equal to the weight of that substance given as W divided by the volume of the substance. Okay, the weight could either be Newton or kilonewton divided by the unit of volume, which is cubic meters, and could also be cubic centimeters depending on what unit you're working with per time. It could also be given as 1 pound per cubic feet. Okay, so this is a standard SI unit for specific weight. You can see that we have specific weight of water given as these values here. You can see that we have specific weight of air given as these values here. The specific weight of water could be 9.79 kilonewton per cubic meters, and for air it could be 12.7 newtons per cubic meters, and you can see the values when we are using pound per cubic feet for both of them. Mass density is another quantity we have to talk about. It is the mass per unit volume. Mass density is given as mass per unit volume. So a mass of the substance divided by the volume of that particular substance is what we refer to as the mass density of that particular substance. The mass density of water is usually given as 1000 kilogram per cubic meters, and then that of air is given as 1.29 kilogram per cubic meters. These are different values. If you want to use slugs per cubic feet, these are the values you're going to obtain when you carry out the conversion. So what you will notice here is that specific weight is given as mass density multiplied by acceleration due to gravity. Specific weight of a substance is equal to the mass density of that substance multiplied by the acceleration due to gravity. And that's what this particular equation represents. The next quantity we should pay attention to is specific gravity. It's a parameter that indicates how much heavier a substance is with respect to water. When you compare a substance to water, how much heavier is that particular substance compared to water or with respect to water? Specific gravity of a chemical, let's say chemical A, and let's represent that with SGA, will be equal to the mass density of A, as you can see here, multiplied by acceleration due to gravity divided by the mass density of water multiplied by the acceleration due to gravity. Eventually, what you would find out here is that the specific gravity of A will be equal to the specific weight of A with respect to specific weight of water. So if you consider these SGA equal to this equation, just these two equations here, G would have cancelled G. This is the mass density of A, this is the mass density of water. So we can make mass density of A the subject of this equation. If we do that, we will end up with mass density of A equals specific gravity of A multiplied by the mass density of water. Again, if we take into consideration just SGA, the specific gravity of A, and equate it to the specific weight of A with respect to specific weight of water, what we are going to be left with is specific weight of A equals to specific gravity of A multiplied by the specific weight of water. All right. So if the specific gravity of a substance is greater than 1, then the material is heavier than water. If the specific gravity is less than 1, then the material is lighter than water. This is how to carry out simple analysis. In case you're working on a project, in case you're working on a question, or you're working on an analysis and you have to compare the specific gravity of a material or of a chemical to that of water. If after your analysis you find out that the specific gravity of that material or of that chemical or of that substance is greater than 1, what that translates to is that the material is heavier than water. And if it's less than 1, it simply means that water is heavier than that material, or that material is lighter than water. Don't forget, we had said earlier on that our weight is equal to mass times acceleration due to gravity. And then we also know that our mass density is equal to mass over volume. Hence, if you say that, if you cross multiply, we can say that our mass would be equal to mass density multiplied by volume. And since we know that our weight is equal to mass, if you put this value for mass into this expression, you will obtain weight equal to mass density multiplied by volume multiplied by acceleration due to gravity. And this would be the same thing as specific weight multiplied by volume, because specific weight is given as the mass density multiplied by acceleration due to gravity, which is exactly what we talked about here. There is an example we can quickly look at to apply some of the quantities that we have evaluated. A reservoir of glycerin has a mass of 1,200 kilogram and a volume of 0.952 cubic meters. Find the weight, the density, the specific weight, and the specific gravity of glycerin. Take your acceleration due to gravity as 9.807 meters per second squared. So let's begin. We know that weight is equal to mass times gravity. From the question, we know the mass is 1,200 kilograms. That's what we have here. And then the gravity is given as 9.807 meters per second squared. If you bring that in here and multiply them out, the weight of glycerin will be equal to 11,768.4 newtons. The B part says we should find the density. We know that the density, the mass density, is equal to mass over volume, which will be equal to the mass we have is 1,200 kilograms divided by the volume. The volume is also given in the question, and that gives us about 1,260.5 kilogram per cubic meters. Then we were asked to find the specific weight, which is going to be equal to the mass density multiplied by acceleration due to gravity. And this would also be equal to the weight divided by volume. And we know the weight already to be 11,768.4. We calculated that. And we also know the volume to be 0.952. If we carry out simple arithmetic operations here, you would obtain specific weight of 12,360 newtons per cubic meters. If you want to convert this to kilonewtons, all you need to do is divide this by 1,000, because 1 kilo is equal to 1,000. That gives you 12.36 kilonewtons per cubic meters. Also, don't forget that if you choose to, you may use this expression to find your specific weight. If you choose not to use weight over volume, you can use mass density multiplied by acceleration due to gravity. What is our mass? What is our mass density? We got 1260.5 multiplied by gravity. That would be 9.8. If you do this, you will arrive at the same value. All right, now we expect to find the specific gravity of glycerin, which will give us specific weight, which will be equal to specific weight of glycerin compared to the specific weight of water. That's specific weight of glycerin divided by specific weight of water. We know that of glycerin to be 12.36, and then we know that specific weight of water is 9.79. That is a given, that is a standard. So if you divide this out, you're going to obtain a value, and specific gravity will have no units because we are comparing two quantities of the same unit together. So the units will cancel out, and then there will be no unit here. All right. As you can see here, this will be greater than 1. What we can conclude is that since the specific gravity of glycerin is greater than 1, that means glycerin is heavier than water. Now let's talk about viscosity. Viscosity is a term that we use when we discuss fluid. When you look at these two plates, you can see that we have two plates here. One of them is movable and the other is fixed. The one at the bottom is fixed, the one at the top is movable. So the upper plate is pulled with a force F. When that happens, you can represent the motion with the diagram you're looking at right at the bottom here. These are liquid molecules which are stationary from the fluid, okay? And then you can see between the two plates there is a height h, which represents the gap between the two plates, the vertical gap between the fixed plate and the moving plate. It is usually referred to as vertical gap or vertical clearance, okay? And then you can see we have a linear velocity profile represented somewhere here, and then you can see we have the maximum velocity. We have these molecules as the maximum velocity of the molecules. So what we can say is that if h is small, now listen to this, this is important. If this height between the fixed plate and the moving plate is small, it simply means that our tau, which represents shear stress or opposing resistance, will be given as follows. We know that tau, as discussed in the previous discussion, is equal to minus mu dv dy. We know that our dv dy is velocity gradient, and we know that our mu here is the viscosity. So if h is small, it simply means that this gradient is constant. This gradient, velocity gradient, is constant in linear profile. But if h is not small, what it means is that the velocity gradient is not constant if h is not small. Don't forget, this tau represents the shear stress or opposing resistance. So fluid offer resistance to a shearing force, and the amount of resistance shown by different fluids is represented by the term viscosity with the symbol mu. So there are two fluids here that we want to quickly look at. We have water and heavy oil. We want to compare the two fluids together. As you can see, we have water here. So, and then we have a fixed plate and a moving plate at the top for both of them. And then you notice that we can represent these. This is our TS of water, which is the shear stress or opposing resistance of water. And this is the shear stress of oil. Okay, when you compare both of them together, because we know that every oil is heavier, we know that oil is heavier than water, what you will find is that the mass density of water is less than the mass density of oil, and then the viscosity of water certainly is less than the viscosity of oil or heavy oil. Here's another example we can evaluate together. A Newtonian fluid is contained between two parallel plates 1 millimeter apart. Lower plate is fixed. Find the velocity gradient if upper plate is pulled at a velocity of 1.22 meters per second. Then secondly, find the dynamic viscosity if the shear stress on the plate is 3,447.5 Pascal. Don't forget, viscosity is equivalent to dynamic viscosity, and this is equivalent to absolute viscosity. Any of these three terms can be used interchangeably. So you have to know exactly how to apply them. Viscosity is equal to dynamic viscosity, and it's also equal to absolute viscosity. Let's quickly analyze that question. We have a fixed plate right at the bottom, and then we have a variable plate, a movable or adjustable plate at the top. And then we've been given from the question that the velocity of the upper plate is 1.22 meters per second. We were told that the vertical gap or vertical clearance between the two plates is 1 millimeters, and that can be converted to meters as 1 times 10 raised to the minus 3 meters. And then you can see we have the constant resistance or constant shear stress can be applied from this side. We know the v dy is our velocity gradient, which is constant, and that will be equal to change in v over change in y, which will be equal to v top minus v bottom over h. Our v top, we know it to be 1.22. Our v bottom evidently will be equal to 0. If you subtract that, this is what you're going to have. The velocity gradient will therefore be equal to v top over the vertical gap or clearance, which will be equal to 1.22 meters per second divided by 1 times 10 raised to the minus 3 meters. Meters will cancel meters, and what we would have left here would be 1,220 per second is what we're going to have here. Okay, now we know that our shear stress is given as viscosity multiplied by velocity at the top divided by height from what we have calculated at the top here, because this is normally supposed to be dv dy, but we found out that dv dy is equal to v top over h since v bottom is equal to 0. So we have that expression here. If you make the mu, which is our viscosity, subject of this formula of this expression, you have mu is equal to tau, which is the shear stress, divided by v top over h. We calculated our v top over h as 1,220 per second, and we know that our shear stress as given in the question is 3,447.5 Pascal. So if we divide this would give us 2.82 Pascal seconds. I would encourage you to go over this video again and again and again so you can understand the concepts that we have explained with the physical quantities discussed and then the examples that we have evaluated together. This is the end of this lesson. In case you have not subscribed to this YouTube channel, I want to encourage you to quickly do so now. And if you love this video, don't hesitate to give it a thumbs up. I'm interested in reading your comments. What do you think about the subjects that we have discussed? Is it an easy subject? Is it a difficult subject? Is it something that you feel you have a proper grasp of based on what we have discussed in this video? If your answer is yes or no and you want to provide an explanation, please do so in the comment section. I'd really love to read from you. Thank you once again for watching. See you in the next session.